It gives us a sense of scale of the area we're moving in. Scrolling. While being most common with platformers and other side-scrolling games, I'd argue it's even more important to have it in top-down games. It helps build sizable worlds in shooters and alike, and it's essential in strategy games as the given space on the Scratch's canvas is not enough for maneuvers and decently large battles. Things normally can't go off-screen in Scratch, but there are some universal workarounds to this that are used in every scrolling game. However, with this, you can't detect any collision or enact movement or shooting properly. Of course, there are projects that do this, but this requires knowledge of very advanced maths. Since I am one of the less mathematically inclined, I created the OASIS-Engine, short for Offscreen Action Scrolling in Scratch. I'll walk you through the theoretic part and how it works, plus the pros and cons and which games you should use it for. The basic idea of the OASIS-Engine's theory is that you work with normal scrolling, but all collision, shooting and so on is handled on a minimap that shows you the entire level. When I started working on the engine, I changed the technical language a bit. The principal system stays the same. So in OASIS, you have a simulation layer. This depicts the entire level and the simulation objects, such as the player and AI, move and do all other logic like shooting, getting hit, etc. They write their stats like position, rotation, etc. into lists. A virtual camera moves around. This info is then used on the zoomed in graphics layer. As the name suggests, the objects handle the visual aspects. They move to a position relative to the virtual camera and the zoom. It also runs on a frame/tick system so that it can run smoothly at a consistently high frame rate. The way that the system is structured also allows you to program a game on the simulation layer only and then add the entire visual aspect with scrolling later on. So let's jump right into how it works. So, when you start the game, this block runs. It's in the game controller/manager, which handles all basic logic in an object-oriented programming style. So when you click the green flag, it broadcasts that the game has started and then waits for all sprites that receive this broadcast to enact the script under it. And when this is finished for all sprites with the broadcast block, it then continues to forever broadcast frame. The thing within the forever loop runs once a frame, and so with the maximum of 30 frames per second in the Scratch basic version, it broadcasts a frame exactly once a frame. Next to the simulation camera. This, as you can see, is the virtual camera that is responsible for the moving and all. If I quickly hide the visual layer, you can see that this also moves around and if I now show this sprite here, you can also see that when I'm directly over the sprite, it's directly in the center, and when I move to the left, the middle of the screen, which is the camera, also is relative to the left of the graphical unit here. So the scripts in this are relatively simple. When the game starts, it goes to the back layer and enacts a couple of variables that set all of the camera movement. These are labeled by cam underscore in the variable tab. The first one is the zoom, which is set to 3, which means that each thing on screen is 3 times the size of the simulation layer. As you can see, this here is 300%. And this just is the magnification basically. And all of the other ones are set to 0, These are for camera position and are centered, therefore. Each frame, it then runs this custom block that changes the camera position with a speed of 5 and a smoothing value of 7. This runs this block. It first changes the simulation camera X and Y by speed times the right or D key pressed plus left arrow or A key pressed times -1. This block here basically just looks whether the right arrow, whether it should move to the right or to the left. And if both keys are pressed, it just stays at 0. When just, for example, the right arrow is pressed, then it says that this is 1. And if I press the left arrow, for example, it says it's -1. This then gets multiplied by the speed and therefore changes the x-axis of the position on the x-axis of the camera. The same here happens with the y-axis and y position, and these values are then inputted into the smoothing thing, which then takes the current camera simulation position minus the camera screen X and Y, and these are just there to basically smooth out the whole thing with the smoothing value. And then for clarification reasons, the camera's physical position in the world is also changed. This can then also be used, for example, for three-dimensional sound, with the camera being basically the thing that listens to the sounds. Next we have a simple simulation unit, which is just as a placeholder and should show how it works. So when you broadcast game starts, it deletes all of the list values that are used to store the stats for the direction, the X and the Y. It then hides the sprite, goes to the back layer, sets a position, and the ID is basically just for identifying whether which slot of the list is for which clone. Then a loop gets enacted that just sets these values, creates a clone of itself, and changes the ID. And at the end, the ID is set to sprite to tell the sprite that it is no longer a real clone, but instead that you handle the sprite, which is important later on. Then when it starts as a clone, it switches the costume to unit and shows itself. And this is basically all code in here, as this only acts as a placeholder in the moment, and in later tutorials we will build upon this as an example. The simulation wall is just the colliders, as you can see. In here it's all of the colliders of the scene, and it is used on the simulation layer, and units can collide with it and check whether they are hitting a wall or not. It is centered and visible and at the back of the layer. Now to the graphics unit. This is the graphical representation of the unit on the simulation layer, and as you can see, it moves relative to the map's position. So when the game starts, it creates the same amount of units as there are in the simulation units by checking for the length of this. It also has the same function with the ID and the sprite to then reference the place in the list, or say that it is not a clone but a sprite. In the frame, it then hides to commemorate that any sprites may be there. Then it checks if the ID is not sprite, so if the object is not a sprite but a clone. And then it goes to the item ID of position simulation unit X times camera zoom minus cam screen X. And the same for the Y, which is just the formula to position it relative to the camera position and zoom on the screen. And it then points into the right direction. It sets its size to camera zoom, which is 3 times 100, which just shows that the zoom is the magnification only, and you have to multiply it with 100 to get the exact size. And then it shows, it goes to the front layer, and if it is touching the edge, it then either changes its ghost effect by 25, so gets less visible or more visible. This can be used when things need to go off screen smoothly. So you can see that it doesn't just plop away, but it is rather smooth in transition. And this is enacted every single frame, so it always happens every single frame it is updated. When the game starts, this graphics background goes to the front, shows and goes to 0, 0. And when it receives frame, it needs to change its size. However, there is a size limit in Scratch, so a map of the dimensions like this with 618 times 618 wouldn't work. So we use a simple size hack, which is, if I color this here in with a color, you can see that this is a relatively small one. And if we use this and set it as the costume, then set it as set the size to it, it still is a valuable, it still is an acceptable value. And then we just simply switch to the map sprite to use the enlarged version, the real one, and can achieve sizes of up to 300% and more through this simple trick. And the map sprite is of course a one-to-one representation of the simulation layer. You can also make it even larger, but then you would have to manually modify this here. So it is a one-to-one representation of the simulation background of the simulation. So if we take this here and copy all of these and paste them onto the map, you can see that the colliders line up with where we want walls in the map. This has to be one-to-one so that there is no weird things happening with the map. And it then sets its X and Y to 0 minus screen cam X and screen cam Y. And there we can see we can scroll around the level smoothly. The unit hides and shows when on screen, and if not, it of course disappears. And this is basically all you need to do. And this is how the engine works, and it's pretty simple to understand. It's not very large or complicated. However, there are a few pros and cons we need to talk about. So, the pros are that collision and logic is not limited to what is on the screen, which is the main point of the engine after all. It's also easy to use, and there will be plenty of tutorials coming in the next days, weeks, months from this channel. And there also is plenty of room for possible features and plenty of possibilities in how to use this engine to the best of your projects. The only con is that less of the 300 clones, which are the limit in Scratch, can actually be used, as for each clone on the simulation layer, you'll have to keep in mind that there will need to be one for the graphic layer too. So when you, for example, have 10 units, then you need to account for 20 clones, as you will have 10 units on the simulation layer and 10 on the graphics layer. And now we just quickly dive into which games the engine is most valuable for and which games do not profit as much of it but can still use it. Generally speaking, every game for which you want a larger map but collision off screen, this engine is best bet usually. And one of the things that of course greatly benefits from this scrolling engine is strategy games, which wouldn't be possible without an engine like OASIS, since you need to also detect units moving or fighting off screen, which is just not possible with the normal workarounds to scrolling. Shooters can also use this for AI to dynamically move around the scene and even shoot the player from off-screen without needing to write specialized code for off-screen movement and shooting. And open world games can also benefit from the dynamic AI, although this is not a requirement and you might be better off with using a simpler system due to the lower clone count, which could also hinder your game. All in all, I really use this engine as often as I can, and for example, it is the main engine used in Star Wars Battlefront Scratch, which enables the AI to dynamically move around the scene and capture command posts, for example, without them just having randomized scripts. And for example, for strategy games, I use it for my Total War battle engine, as it also needs to have off-screen fighting, and you can zoom in really far and see how all of this works and the single details on all of the units. I hope you liked this video and it will help you with your further game making process. If you, I'd really appreciate a like and a subscribe. All source files will be in the description, and see you in another video. Special thanks of course to my supporters, Bamfux, Blueblur 2021 and +1.